Hi and welcome back to Extreme Academy Live. This is part 2. If you didn't see part 1, don't worry, the recording's available both in Vimeo and YouTube. You can catch up whenever you want. Welcome to this week's live session. Now last week we learned all about some of the basics of communication, so bits and bytes and binary, and how communication happens through our systems through pulses of electricity. We also covered types of networks, and this week we're getting deeper into networking technology, and Isaac will tell you all about that shortly. So just a reminder, if you want to interact with the team, if you want to ask a question, want to take one of the quiz questions, then just log onto the app with another browser or through a phone. The QR code should be appearing just over my shoulder and the URL on screen. We've got a team of extreme engineers and partners from our extreme academies and our training partners there to help you. Now I just want to say a big thank you to everybody who responded to the customer satisfaction survey. It was really important for us to ask you what you thought, what you wanted us, what you liked, what you want us to do better, and we've been reading through those responses this week, and I guarantee you that we will be taking your suggestions on board as we go through this course and on into 2021. Now, there were a few common questions. There was a little bit of confusion last week, so I thought I'd cover a couple of those before we get going into this session. And there's a little bit of a theme here. So we had some questions like, what is Nando's? Why does Isaac keep talking about Nando's? Why don't I have a Nando's in my country? Well, for those that don't have a Nando's in your country, Nando's is a chicken restaurant founded in South Africa, I believe. I mean, you'll tell me if I got that wrong. Famous for its spicy chicken recipes. Why don't you have a Nando's in your country? We can't help you with that. That's hopefully when you start traveling again, you'll be able to find a Nando's and check it out. The other question we got often was, where can I find the recordings of the sessions? Now the recordings, because we're going out live, we're streaming live, the recordings will appear probably 5 or 10 minutes after we finish the live stream in the place where you were watching. So they'll appear in our YouTube channel, they'll be in the Vimeo page that you may be watching on. They'll also stay within the streams of Facebook and LinkedIn. To that point, we didn't actually mention it last week that we're actually going out on 4 channels, YouTube, Vimeo, Facebook and LinkedIn, because when we were going live last week, we weren't 100% sure that everyone was going to fire up at the same time. It worked absolutely perfectly. The technology was really smooth. So it's all part of our philosophy of making this training free of charge and trying to push it into as many corners of the world we can. So you can decide where you want to watch it. If you might be watching this on Vimeo right now, but you could actually get YouTube running on a smart TV or a games console, and that might just free up a screen for you and give you a better learning experience. So it's absolutely up to you. You can choose where to watch. Okay, it's time to bring in Isaac now. I've got this monitor that lets me see Isaac getting ready. He's got a hat on this time for some reason. I don't know why. He's about 50 miles north of where I am. It's not that cold here in the UK, so we may find out why he's wearing a hat today. So we're ready to go. Claire, if you want to run the graphic, and let's bring in Isaac.
Wow, what a response we had last week. Just fantastic. Thank you so much for all your comments, for all the questions that came in. Thank you for reposting us on social media. Thank you. This has been absolutely fantastic. We had a target to train 50,000 people. This is the first class, and this will be the first class of many. And we will hit that target, and we will help lots of people. So if you've been helped, you enjoying the course, continue, let us know, continue posting, use social media, LinkedIn, wherever, hashtag Extreme Academy Live, Extreme Networks, go for it, spread the word, tell friends, tell family. The more the merrier. We can handle that. just fantastic. I am so privileged. I work with Rowan and Claire. And I work with such a great team, and this is a great team effort. So let's get down to it, right? Again, I'm coming to you from Cambridge, very famous city, one of the oldest universities in the world, probably the best university in the world, where a certain gentleman by the name of Stephen Hawkins, right? You remember Stephen Hawkins? Yeah, great scientist. He invented the black hole here in Cambridge. It's fantastic. You this place is so full of science. It's pretty amazing. And this time I'm not looking at the monitor so that I can ignore in case they tell me that he didn't actually invent the black hole or whatever it was. So, where are we going to go today? Well, last session I told you when we started that generally speaking, when we talk about this academy course, let me just check the time. Okay, right. When we talk about the academy, when we talk about networking, we generally cover what we call the OSI model. Some people refer to it as the Aussie model, OSI model. And I said to you that my approach was I wasn't going to do it immediately in the first session, right? I've read about the OSI model and studied it for years, and I still think I know nothing about the OSI model. It's not the easiest of things. I didn't kind of want to throw it in right at the beginning. So we will kind of, we said, I said that I would start basically with the layers, because I said the Aussie model is made up of a whole lot of layers, 7 to be precise. And I said, I'm going to start with layer 1. And the reason I did that is because layer 1 is really important in the sense that when we spoke about binary, and if you haven't watched the first episode, go and watch that on binary, because that's really interesting. But the outcome of binary, of converting numbers and digits into zeros and ones, means that we can add an electrical pulse. We end up with an electrical pulse, right? A negative or positive. And once we put that on the wire, we can transmit data. Right, and that's what we're talking about. We're talking about networks and the ability to transmit data from one place to the next. So I wanted to cover that so that conceptually you understand that when you hit send on an email, when you hit any button on an application to do certain things, it's going to go through this whole OSI model. And the last model, the last layer, layer 1, is the one where everything is converted into zeros and ones, and or onto electrical signals, and from there off it goes. So now that you've kind of conceptualized that, I want to go back into the OSI model. Now, people study this at university sometimes for years, right? So I want you to understand that I'm not going to teach you degree level OSI model. I'm actually gonna skip over it, not skip, but I'm gonna cover it quite lightly. Most of the times that I've been taught or read about OSI model, people want to try and get you to remember what the name of each layer is, and it's this name, and you got to remember with this anagram and that anagram, and all of that stuff is okay, but it's more important that you learn the concepts of what we're talking about here, because the OSI model is not a piece of hardware, something like a network card. You can touch a network card, you can touch a computer. An OSI model you can't touch. It's a concept to explain how data moves in a network, and that's what makes it a little bit difficult. And so people come up with all these anagrams and things, and if you're that type of a person, if you learn like that, then fantastic, go for it. I'm not that type. I gotta kind of see images, I gotta see pictures, so that I can kind of hook the concepts like on a clothesline. That's how I understand, and I think it's important that you kind of understand that. But if you want to read more in-depth content on the OSI model, oh man, the internet is absolutely chock-a-block loaded with stuff on OSI, and I encourage you to go and do that, right? Don't just think that you can just attend this and know everything there is about the OSI model. It's not going to happen. So read, get books, go online, go watch YouTube videos where they show this information, and don't just sit with one a person explaining to you in detail the OSI model. Get different views from different people, because all these instructors, they might have slightly different focus points, and they might help you to build a really good model in your head of how this works. So we started with layer 1, and right up at the top is layer 7. The way I kind of think of it is like a sandwich, right? You have the bottom of the sandwich, there's a layer of bread, there's a layer of bread on the top, and then in between is all the filling. That's how I kind of like to think about things like that. So we spoke about the layer of bread on the bottom, and I'm going to go over all the layers now, rather quickly, if you want to say that, and then we will cover them a little bit more. I do want to focus on layers 7, 6, and 5, 6, and 7. I want to cover those because there's some important stuff that happens there, and if you don't kind of understand that, some of the other stuff is going to be really difficult to grasp. Things like HTTP, things like DNS, which is really, really important, and it operates on those layers. We've already covered 1, and then after we finish this session, we'll go into layer 2. So layer 1, 2, 3, and 4 in networking terms, those are really, really important layers. I'm not saying that the other 3 are not, but those ones, when the heavyweights do troubleshooting and things like that, those are the layers, and those layers we will focus on in further lessons as we go along in more detail. So let's start by just me typically reading a slide, because it just helps me. And so we're going to be talking about data communication fundamentals, the fundamentals of data communication. What's data communication? Well, point A, point B, let's talk. How do we talk? The really interesting thing about this is that the guys who designed this, people like Vint Cerf and so, 40 years ago, maybe even more, the foresight that they had was absolutely incredible. But when you really study this, you kind of discover that everything they did was really based on human communication. They looked at the way that humans spoke to each other, that humans communicated, and they kind of created a digital version of that. Said, well, if humans talk in this way, let's make computers talk in this way as well, because it's really quite efficient. So a lot of these principles over here, as we go through them, you will hear me relating them to the way that humans communicate. And that should really help you to get around some of these concepts. It's going to be a little bit scarier than session 1. By that I mean, we're going to dig a little bit deeper, right? The first 2 inches when you dig, that's really easy. When you go a little bit deeper, you got to do a little bit more work. But I'm completely confident that you're going to be able to get the stuff. There's nothing here that is rocket science that you're going to say, no, I'm giving up, I can't do this. No. It's not like that. So let's get a little bit deeper. Let's jump into this. Now, one of the very first things that's very important for us to talk about is to talk about protocols, okay? Protocols. And I'm going to define it by reading what it says on the side. It says, a protocol is a set of technical rules that control the exchange of information between different computers or computer networks. I think that kind of says it all. And I could go ahead and read what this slide is here, but I'm not going to do that because we have one of our senior engineers. I mean, this guy is such a great engineer, but not only is he that, he's a fantastic teacher, and he did a video recently which you can find on the Extreme Networks YouTube channel, and in it he describes protocols and he uses Queen Elizabeth as an example. And I instead of reading this and going over this, I think it's just better if we go to the video. It's GT Hill is his name. And there's tons of videos, on our YouTube channel where you see GT Hill teaching, and I mean, he really simplifies it. I love listening to the guy because I learn from GT Hill. So Claire, I think you've got. I asked you to line up that video clip. So this is something that's already been recorded. This is not live, but we recorded it. It's a great video. So Claire, if you don't mind, can you just layer it and let it go? Thanks.
What's the right protocol if you get to meet the Queen of England? You're going to want to find that out. Hit that subscribe button, hit that notification bell. Here we go. Being from the United States, we don't spend a lot of time thinking about what we would do if we got to meet the Queen of England. But if we ever did, we need to know the right protocol, the right things to do in order to do that. First, I'm reading here to make sure I get this right. A curtsy or a bow, the head only. Address your majesty and subsequently as ma'am. Don't speak unless spoken to. And don't sit until she sits. And don't eat until she eats. These are things that are the right protocol for when you meet the Queen. Protocols also exist in networking. So we've heard of these before, maybe you haven't, but there are many, and I mean by dozens, if not hundreds of protocols inside of networking. So a protocol, it's a set of rules for how to communicate with each other. For example, some protocols need an acknowledgement. So if I'm going to talk to Sam, I may say, Sam, how are you doing? He may acknowledge that he heard me before he even responds. That would be part of a protocol. Or maybe I just send Sam a lot of information and I get no responses. That also is correct rules for other types of protocols. Lots and lots of rules that exist for these, some that you'll need to know and some that you don't have to worry about so much. Some example protocols, one of the most important, is called TCP/IP, Transport Control Protocol / Internet Protocol. It was invented way back when. It's really what is the primary mechanism for data movement today. If you are streaming this video off of YouTube right now or off of any kind of other provider, that data is being sent to you over TCP/IP. Now, in order to get that data to you, it likely also had many other protocols in use. What if you had to log in first? What if maybe you're at a university and you sat down and you had to log into your local network first? That was done with a different protocol. What if you need to transfer files or you need to get your email? All of that is separate protocols. So a protocol is just a set of rules for standardizing a way that devices communicate. There are some protocols that are just for networking devices. So at Extreme Networks, let's say we have switches that want to communicate with each other or a switch to an access point. Those are all done with other kinds of protocols. Now, don't worry so much. You don't have to memorize all of these. You don't have to understand the bits and bytes of how they work. But generally, you do want to understand the basic rules for some of them, the more popular ones like TCP/IP. We're not going to go through that now. But for now, I just want you to understand a protocol is just a way that devices communicate. There are hundreds and hundreds of different protocols. That's what I want you to understand right now. Hit that subscribe button, hit that notification bell, because we're going to want to keep going here. Thank you again, and we'll see you in the next video.
Awesome. See what I said? It's, you listen to the guy and it's like, wow, I understand protocol. So I don't need to spend any more time on this because I think you've got it. And like you said, there are hundreds of protocols that we use. Just like in human behavior, the way we talk, it's exactly the same. There are these different protocols. So we talk about protocols, but you will hear people say things like, oh, we talk about, the TCP/IP protocol, transmission control protocol, internet protocol. They call it a protocol. It's actually not really the right thing to call it. It's more accurate to call it a protocol stack. A protocol stack. What's a stack? Well, it's like when you have a stack of things, like when you have a burger, there's stacks of fillings. There's burger and cheese and gherkins and lettuce and tomato. There's stacks. There's a stack of things. And so when you hear us talk about the protocol, it's the protocol stacks. Yes, within the stacks are various protocols, but the OSI model really is a protocol stacks, different layers, and each layer is made up of various protocols. So that's what that term means, the protocol stack. Now, what's the purpose of layers? And here in this diagram that you can see that we've kind of drawn out just two layers. So in this diagram, we've drawn out two layers. The one is the physical, right? The physical characteristics. And you always need the physical because it's like if you are delivering something, if you need roads, you need a railway, a train needs tracks. That's the physical. That's what gets you from one place to the other, the physical. So when you're trying to talk about, how data moves, one of those components has got to be the connection. Now, physical, yes, that could be Ethernet, that Ethernet cable we spoke about. It could be the fiber optic cable. And of course, it could be also wirelessly. Even though wirelessly doesn't have a connection, it's photons traveling over the air, it's still considered a physical connection because before it becomes photons, it's got a device that converts those things into these photons that travel, or radio that travels through the air. So that's the physical part. The other part, the language and behavior, those are the protocols that together they combine to be able to get the data ready to then go onto the railway tracks, right? So in this simplistic example, we've kind of mapped it as two, and we said, this is a box with a protocol stack, and at its most simplistic, it's two. It's the medium, the tracks, and then the rest of the protocols, the software, the intelligence that gets this package ready to go into the train so that it can be taken from point A to point B. We sometimes refer to that as the physical characteristics on that bottom one, the green one, and then the language and behavior is on the one above. The truth is, it's not really two layers. The OSI model is made up of 7 layers, but I guess that the top 6 can be kind of encapsulated, into one, just to show the distinctness. Now, this protocol stack is really responsible together for managing the communication, right? Once they've sorted everything out, the result of everything is they put it onto that physical layer where it goes out, for example, on the network. When you when you create an image on your computer, be it at home or whatever, and or in the office, and you need to print out an email with an image or with a network diagram, you do everything on your computer. You set it up, you use Visio or whatever tool you do all of that, and then when you press print, it goes off on that railway track. It goes off on that Ethernet cable off to the printer to go and do what you need it to do. And generally speaking, you want it to be accurate, right? You don't want to send a picture with a red circle in it and it comes out green on the other side. No, that wouldn't be cool. So accuracy is important. We need to do that type of stuff. So if we're talking about networks and if we're talking about data moving from one point to the other, then let's think about this in human terms. How do I move data how do I communicate with somebody that's halfway around the world? Or I'm in Cambridge. How would I communicate with somebody in Oxford? Okay. How would I do that? Let's say I didn't have any of this technology available to me pre-internet. I mean, you can see by my beard, I was born in an age where there was no internet. Can you believe it? I was born in the age where we had something called fax machines. Like, it's old, I know. But if you wanted to communicate with somebody in a different city, in a different town, maybe in Wales, a different country, how would you have done that? You would basically have needed a few things to be able to do that. Now, we would have probably communicated using letters, right? We would have exchanged letters if we didn't have telephones and stuff like that. But if we break it down a little bit more, what we really would have needed would be addresses, right? So my mum lives in South Africa. I happen to know her address. Now, she doesn't know how to use email. She knows how to use FaceTime, and that's about it. She doesn't know how to use email and compose and draw. It's just, too beyond her. It's just like, wow, no, that's too complicated for me. But if I know her address, I can send her a Christmas card. And if she knows my address, she can send me a Christmas card. So if we wanted to exchange information, we would use addresses. They would be really important. Yes? Agreed? Hope so. Same thing with computer networks. To send data from one computer to the next, you need addresses. Both computers need to have addresses so that you can identify where that computer is. Now, it's not the same, and it's certainly not written the same way as the addresses for my mom, okay? But the principles are the same. So let's look at what you would need. Every device has to have a unique identity, okay? If I sent if my mum had an address, and that address was duplicated or triplicated in South Africa, that would be a problem, right? She lives in a street called Wellington Avenue. That's the name of the street. But that's not the only Wellington Avenue in South Africa. There are other Wellington Avenues. She lives at a particular number. And there are other people who live at that same number in Wellington Street, but somewhere else. She lives in a particular town, and somebody else could live in the same street address, same physical name of the street, but in a different town. But you couldn't have two exactly the same, because who do I send it to? So that kind of makes sense, right? Every address has to have uniqueness about it. And if you think about a letter, they do. They have postal codes, etc., etc., etc. So in computer world, we need to do the same thing. Because if we have duplicate addresses, who does the email go to? Who does the request go to? It can't. So every computer needs to have something like that in order to communicate accurately. So let's look at this. We have a computer in London. We called it PC1. And we have, and we call that the source. And we have another computer called PC2, and that just happens to be in Lisbon, okay? And that we would call the destination computer. I have an email, I have a WhatsApp message, I have a, whatever it is, Skype message, whatever, Facebook message, whatever it might be that I want to send from the source to the destination. So I have some data, correct? I have some data that I want to send. That data has a address, which is PC1 in London, right? So conceptually, it's PC1 in London. Now, I know there are millions of PCs, I know that, but conceptually, PC1 in London. And I need to send it to PC2 in Lisbon. So PC2 Lisbon would be the destination, and PC1 London would be the source. Okay, and basically that's what I would need to communicate. I need addresses. Yes? Perfect. Now here's an email, right? I need to send an email from my computer that's going to end up going to somewhere else. To be able to do this, I need an app, an application. Now, a few years ago, before Apple came around with the iPhone, we didn't really call these things applications. We called them software programs. Okay, that's the term we use. These are software programs. So Apple came around and stopped calling them that and called them applications, and then shortened it to apps. And today we talk about everything apps. If it runs on an iPhone or an Android phone, it's called an app. If it runs on your computer, we just call it apps. So there's an app, most of you would know it, called Microsoft Outlook, and we use Outlook to compose emails and send emails, especially in the corporate environment. So my computer is running Outlook, and I want to send an email. What happens? Well, I type it up, I put the address in, I put all of those things in, and the computer starts doing things in the background because it needs to use a protocol, right? It uses a protocol. So on these layers of the OSI model, this is how it relates to the OSI model. On these layers of the OSI model, the protocols operate, various protocols operate on the different layers. And one of them that operates is called SMTP, Sierra Mike Tango Papa. And it stands for Simple Mail Transfer Protocol. Somebody thought to call it simple. It can get complicated, but Simple Mail Transfer Protocol. And when you press the send button, then Outlook is going to use the SMTP protocol to send that message to the other side, and it will use that on the layer 7 SMTP protocol. And that protocol or that SMTP protocol is operating on something that we call port 25. Now, the first time that somebody explained this to me, I just didn't get it. Like, what are you talking about? A port is like a harbor. How does a computer relate to a harbor? I just kind of didn't get it. And then a good mentor friend of mine said, well, think of a port as a hotel room number. If you stay at a hotel, anyone might know if you know that you stay in at the hotel. If somebody watches you, they can see you going into the hotel and only coming out the next morning and then going back into the hotel again, after spending time at the beach. So they can deduce that you are staying at the hotel. But they don't know which room you are staying in. Okay? It's like they don't know. And if they go to reception and say, where's Mr. Diabru staying? The reception's going to say, sorry, sir, that's private information. But think of the port number as my hotel room number. Okay? So if you know the hotel and you know the hotel room number, you can get a message directly to me. You can put it under the door. Yes? And so SMTP uses the hotel room number 25. There are many different ports that different applications use. So if you were using another email program, whatever it might be, it would still use port 25 because that's the protocol used to send mail from one location to the other. There are other protocols as well. For example, HTTP. You guys have all typed in HTTP on the browser. That protocol uses port 80, right? And if you use HTTPS, which by the way doesn't stand for the plural of HTTP, HTTPS stands for Secure HTTP, and you will see that every time you connect to Gmail. If you type in HTTP, gmail.com, watch your browser. It changes from HTTP to HTTPS. So it changes from not secure automatically to secure. The same thing with banking, and most sites that carry personal information are HTTPS. So HTTP port 80, and that's a standard port. Port 443 HTTPS. It's a standard port. Everybody knows how to use that. There's another protocol used as well for mail, for retrieving your mail, and that's called POP, Post Office Protocol, and that one works on port 110. So I think I've explained what ports are. Ports are not necessarily tied to an application, so it's tied to a protocol. So Outlook is just an app, but it's an app that sends mail, and the protocol to do that is SMTP, and SMTP uses a particular port number, and the case in here is port 25. So here I have my source computer, I have an email, I have a destination computer. It's coming from mine, port 25, and it's going to go to the destination, port 25, right? So it knows it's an email, and email travels on port 25. So it now knows I've got data, I've got the port number, so I don't know that they're using Outlook. They could be using any email program. It doesn't matter, but as long as that program is using port 25, they will receive the email that I sent them on that program, right? It's that easy. And that's one of the reasons why we use these protocols, because if we didn't, could you imagine how could people deliver? Because someone would write an email program on port 25, and somebody on the other side of the world would decide, no, we're going to use port 111. What would happen to the email? You'd never get there. So protocols standardize and allow different vendors, different operators, different whatever, as long as they use those same rules, everything's great. So here I have my source, right? I have my destination, and I know which port it's going to on a destination. When I press send, bam, off goes the email, and someone on the other side gets a little envelope that goes bing, there you go, you have an email. Fantastic. Okay, now OSI model, this was designed in 1984. They started talking about this. Now remember, I told you this is not a hardware. This is not a piece of hardware. That's not what it is. It's a conceptual model. One of its main purposes, right, was because it stands for OSI, stands for Open Systems Interconnection, and one of its main functions was something that people saw really early on the advent of the internet, is that vendor A made a switch or a router or one of these devices, and they said, we're going to use this protocol and we won't talk to anybody else. And so if we're going to make our product so good that everybody's going to buy this product, and what we'll do is we'll just make sure that it only works with our equipment. So if you buy this product, you're basically stuck with us. You can't go anywhere else because it only talks to that vendor's equipment. That wasn't a very good strategy. That was just greed, right? Because vendor B might have a better product and it might be cheaper. And if they took the same attitude, then how do you send to each other? How do you communicate? It just didn't work. So by having a open interconnect system, it took away this bad habit of closing things in so that it only works with our equipment. And so today, if you buy a switch from Extreme and you connect it to a switch from one of the other vendors on the market, the ones that don't sell purple stuff, boring, it will work. Why? Because they follow the rules of the protocols. The protocols are open. They are standards. They are open. You'll see later on there's a slide that shows you about these bodies that develop these standards, and then they publish them, and anybody can use them. And as long as you use them, it means you guarantee that if you send an email from one side, it's going to get to the destination on the other side. So that's why these protocols are really important, and this OSI model kind of describes what we do conceptually, so that software development and hardware manufacturers follow this and everything will work. Let's take about 30 seconds just to go and read a little thing here from Ozzy the Owl, quoting Eleanor Roosevelt. I like Ozzy the Owl. He's cool. Okay, so we're back again, and let's look now at these seven layers. I need to drink water constantly. Okay, the first layer we looked at last week. This was the physical layer. This is when we spoke about Ethernet cables, the copper, the fiber, etc. That's responsible for carrying the traffic from one point to the other. That is sometimes referred to as layer 1 or L1, or sometimes you'll hear people talking about the PHY, PHY, PHY. We love, in IT and network, we love abbreviating everything to the point of no one understands anything. But when you see people talking about the PHY, it's just short for physical, physical layer. That's there's no protocols that are really operating on this layer, TCP/IP protocols. So layer 1. Layer 2 we call the data link layer, and once we finished all of this, we will jump into layer 2, and we will cover that in a lot of detail. So in layer 2 we deal with something we call MAC addresses and switches. These switches, remember that purple switch I showed you? That operates on this level. What's a MAC address? I will cover that as well in detail, but remember when I told you about those two PCs, the one in London and the one in Lisbon? Both of those PCs have what we call a MAC address. It's got nothing to do with Windows, even with Apple, even though all Apple devices have MAC addresses. But guess what? All Windows devices have MAC addresses, and all Linux devices have MAC addresses. So we will cover that. I think of a MAC address like a passport, but I will cover that in more detail. So they have MAC addresses and switches. These devices like those 24 ports and 48 ports that we spoke about last week, they operate on this particular layer. And I'm not going to spend too much time here because we will come back to this. You'll see that there's a couple of protocols that are linked to this layer, like ARP, PPP, and again we will cover that. Layer 3, we call that the network layer. We also can think about that as the IP address, and where IP addresses happen. So IP address is also a type of address. The MAC address, think of it as a permanent address that's been stamped onto onto something. When I used to be a jeweler in my very, very young days, and when you made a ring, a wedding band for example, you had a special punch, and if the ring was made of 18 karat gold, you would insert the punch on the inside of the ring, and then you would just tap it with a hammer, and it would leave an indentation on the ring certifying that the ring is 18 karat. So that's like a hardware address. It's been stamped into that device, and it can't be taken out. It's each device, every iPhone in the world, every Android phone has a very unique. IP addresses are addresses. They are not hardware addresses like that. They are issued to that device. They are issued to a printer. They are issued to your iPhone when you switch it on for the first time. Once you put a SIM card in there, you switch it on, it gets an IP address from your mobile provider. If you do it at home, you switch on your iPhone at home, it gets an IP address from your little broadband, wireless modem at home. So there's a difference between the two. So layer 2, MAC addresses, the one that's hard stamped onto the device. Layer 3, that's an IP address, the one that's issued to that device. You can buy IP addresses, you can assign them. Companies like Extreme buy IP addresses and they own those IP addresses, and all traffic going to extremenetworks.com will go to that IP address. It doesn't really change, but it's not stamped permanently. Okay, so that's what happens on layer 3, and it has its own sets of protocols. Generally speaking, IP, Internet Protocol. The next layer, known as layer 4, the transport layer. So it's responsible for obtaining certain levels of quality, and it also can, and by that we mean the communication that computers have between each other. They can be very, very demanding. Okay, so I want to try find the right word. A TCP is a protocol that's got a lot of error correction built into it. So when you send, it's really important, when you send an email, it's really, really important that everything that you wrote in that email goes and gets to the other side the same way that you created it, right? It's like, yeah, it has to. You don't want errors creeping in. You don't want, things to be changed. No, you want it to be accurate. And for that you use TCP. But there are certain types of communication where you don't need that, okay? If you're watching Netflix, so what? So what if you miss, one frame out of 24 frames that make up 1 second? It doesn't care. Your eye can't see it. It doesn't really matter. But it does matter if it's a spreadsheet. It does matter if it's an email. So the control of that happens on this transport layer. Also, port numbers happen over here. So TCP, yes, accurate communication happens on this layer. UDP, where you just broadcast information out, that also happens on this layer. Port numbers, they also added on this particular layer. What's the next one? The next one is what we call the session layer, layer 5. And when you're ready to talk, for example, if you open up your browser and you go http://extremenetworks.com, enter. When you press that enter and the DNS has happened, and I'm going to cover that just now, then you're going to end up on a server, on a web server. By the way, that reminds me, last week I started to talk about servers, what servers were, and I used Gmail as an example, and I said, well, you can't just use one computer in Gmail, you'd need to use thousands or tens of thousands of computers. But I didn't actually say what a server was, and a server is a computer with tremendous amount of horsepower. Right? It's got a lot of processing power in that machine, and that's what differentiates it from the machine you and I use. I'm using a Mac over here. You might be using a Windows machine, a Windows laptop, a Windows desktop. It might be a powerful machine, but a server is much, much, much more powerful. 100 factor of 10, 100,000 times, I don't know, but much more expensive as well. So that's really what a server is. But when you type in that address and you press enter, you will end up on that IP address of that server. You will end up knocking on that server saying, excuse me, I've been told you are extremenetworks.com. Can I come in? So the server on the other side is going to say, well, let's communicate. There will be a protocol. It doesn't just let you in. It needs to establish a protocol. The best example of that is when I phone Manuel. When I phone Manuel, I say, hi Manuel, is that you? And Manuel acknowledges that and then says, Isaac, is that, yes, Isaac, yeah, it's me, Manuel, yeah, is that you, Isaac? And so I asked for Manuel, he heard me, acknowledged me, and then he sends me, is that you, Isaac? And I say, yes, Manuel. So there was a protocol that happened at the start of our conversation. Once that protocol is finished, our conversation can then go on. Same thing happens when you establish communication with a web server, right? You knock on the door, you start this communication backwards and forwards. Once that has been established, are you Extreme? Yeah, are you so and so? Okay, let's start chatting. Then we have a conversation. Make sense? Great. There's a video that I recorded, and it's on LinkedIn and here as well. I think it's called Shaking Hands on the Internet. That also explains it. So that's what happens at session. It establishes a session, and then it goes. It's also responsible for stopping a session. So it will start the session when the conversation is over. It kind of presses that red button, like on your phone, says cool, bye, and the session brought down, thank you, waiting for the next session to come through. By the way, a server can handle thousands of sessions at the same time, because that's going to happen in the real world. On a telephone call, it's not quite that simple, although you can do call conferencing, right? So that's layer 5. Layer 6 is the presentation layer. So this is quite interesting, because when you've typed that message that you want to send to somebody in an email, presentation layer is going to do a number of different things. It's going to take what you wrote as text, and it's going to change that into ASCII. Remember last week I asked you to go and do some homework about ASCII? Well, this is what actually happens. It goes to change the text that you wrote into binary. It's going to break it down into binary, into zeros and ones. So you can kind of say that it does this translation from the language that you understand. It breaks it down, converts it into zeros and ones. So it does translation by breaking it down into a language that the computer understands. It also formats the data, so it puts it in the right format, so that when it sends it, the application that opens it knows the structure and knows what to do with it. And it also does encryption, right? If the CEO of Extreme Networks sends an email to another CEO concerning particular business, concerning whatever it is, they want to make sure that that data is encrypted. What do we mean encrypted? If you've probably heard this term and you might not know. It scrambles the data in a way that only can be unscrambled on the other side, so that nobody can intercept it, right? So it secures the data. That's what that encryption means. It secures it and then sends it down that pipe. Remember HTTP, HTTPS? The S is not plural of HTTP. The S is secure. So when you connect to your bank, it is a secure connection. That information is encrypted. The same thing when you connect to Gmail. It is secure. Yes, it is encrypted. The information is encrypted. So that's the other thing that happens on this presentation layer. And then finally, we have the application layer. Application layer is not Outlook. It's not Chrome browser or any one of these other browsers. It's not that. It's not Safari. It's not an application. But applications interact with the protocols on this layer. Yes, there is a difference. The application layer is not your browser, but your browser operates on this layer because it uses HTTP, HTTPS, etc. There's other protocols that operate here as well. If you use something like Dropbox, it uses file transfer protocol, or at least that type of technology to transfer files uses this protocol called FTP. That also operates on this layer. So there's a number of different protocols. So you can see from this diagram, as I've built it up, you can see that kind of every layer you can see the protocol stack, what we mean by protocol stack, right? You have the bread on the top, bread on the bottom, and then you have the stack. And each one of these layers has protocols. Now, I've given you on the screen just a few. There are literally hundreds of different protocols, and that makes complete sense, right? If you meet me in the street and you've never seen me before other than here, then you're going to have a protocol. We're gonna have a chat. But Isaac, I remember seeing you. Aren't you the guy on Extreme? Didn't you do that thing? Yeah. Nice to meet you. Shake hands. That's the protocol that we have. But if you're my friend, if I know you really well, we go, hey, how's it, John? Hey, let's go to Nando's. Let's go grab some food. And the protocol will be different. If I were to meet the Queen, I probably wouldn't say to her, hey, Queen Bee, should we go get some Nando's? Yeah, that kind of wouldn't work, right? But you get the idea. Now, in networking, we have this particular saying, and to all my colleagues in networking, I'm sorry if this is going to be offensive to you, but we have this thing in networking saying that says, why make things simple when you can complicate them? Right? Why make things simple when you can complicate? Why just have one model called the OSI model, to describe how information flows? Why have one model when you can have two? People say, oh no, but the second one is to simplify it. It's like, dude, it's enough of a problem to try and remember the first one. Now I got to remember a second one that's supposed to simplify the first one. Okay. The reality is we don't even use the OSI model much, nowadays, but we still refer to it because it's a great model, and every university is going to teach this. So as tough as it is, you're going to have to learn the OSI model. But engineers kind of said, that model is kind of, not that it's changed, but because everything today is done on the internet, we can streamline that. So don't think of it as reinventing, the complicating things. I think it does, but that's not the purpose. Look, these three layers, 7, 6, and 5, in the TCP/IP model, right? So this is the OSI model here, and then the TCP/IP model, they've merged those three into one. Does it make a difference? No, not really. Still using the same protocols across all three. They still do the same thing. Take the packet, translate it, encrypt it. Oh, by the way, I didn't tell you, in the presentation, you also have compression. Right? So if you often see this, you have an attachment, a PowerPoint attachment, it's 10 megs. You attach it to your email, and when you look at it again, it's 8 megs. It's like, what on earth happened? Presentation layer compresses the data to make it quicker to send. So what they've done is they've said, okay, the application layer in TCP describes all three of those. That's kind of, that's okay. Transport layer, we didn't touch. Same thing, TCP, UDP. Oh, yeah, okay. Then they've said, okay, the network layer in TCP, we're going to call that the internet, right? Because the network layer is the layer that talks with routers and IP addresses, and it talks on the internet. So let's just call it internet layer. Okay, that also makes sense. And then they said, let's take the other two, the data link and the physical, let's join them together, and we call that the network layer. So that kind of, it makes sense to me, right? Network for local communication, all of that stuff, switches, great. Next layer, internet layer, when you go outside of your network, outside onto the internet, yeah, that makes sense. Transport layer stays the same, yeah, okay. And let's fold the other three into one. Okay, works for me. Here you can see some of these protocols. So in application data, you'll see HTTP, which is the browser, FTP, which is like for Dropbox, those big files transmitting. DNS, I do definitely want to cover that. SMTP, remember mail? So these work on the application layer. The next layer down, layer 4, TCP or UDP. Those are the main things. If you want guaranteed delivery, you use TCP. UDP, you just stream out. IP, and then the physical is Ethernet, or for example wireless. We use a standard, I think we spoke about this last week, 802.11, and we will cover that in more detail. So on the application layer, once you've taken your message and you compressed it, translated it, and you've encrypted it, and you've done all of those session bits, you take all of that data and that goes down to the next layer. Okay, when it gets to the next layer, it encapsulates the data from the layer above. So you can see in this, it looks like a pill, I suppose, and you can see the top one only has the purple dots. Right now, it goes down to this layer over here, and now we add in some of those different color dots. So we encapsulate them. In other words, we take the first batch, we now add a little bit of flavor to it. Cool. When it goes down to the next layer, now we encapsulate from above, and now we encapsulate again. So as this data goes down the OSI model, it encapsulates from above, yes, goes down, excuse me, encapsulates again, adds, encapsulates until it gets ready to get onto the wire and go out the door. I hope that that's been pretty clear. That's the shortest and the best way that I can describe the OSI model. Like I said, there are tons of people with explanations. I encourage you, go listen to them. You will learn something different from each one of them. Or they are great. So go watch, go learn. Don't let it get you down, because sometimes it can be complicated. You're always going to get these guys who can describe this on the level of atoms, and it can be discouraging because I'm just starting networking, this is so difficult. Ignore those guys, go for the guys that teach the simpler models until you're familiar with it, and then you can build your knowledge. Now, who came up with all these standards? Who came up with all of these things? Well, there's a number of organizations worldwide, right? And these organizations are really important for us. One of them is the IEEE. This you'll hear a lot in computing. I need to finish. The IEEE, well, they are involved in things like they call the International Electronic and Electrical Engineering, I think, Institute of Electrical and Electronic Engineers, and their job is to set standards. So they will set standards for electrical, positive and negative. They will set standards for electronics, all sorts of stuff. They are the body that oversees this. There's the ISO. We know all about the organization, International Organization for Standards, to have standards for all of these things. So there's a number of these different ones. The IETF, that's a really important one. The Internet Engineering Task Force. They make sure that the internet works. It's not only them, there's others, but these would be the most important. And this, I suppose, might turn up an exam question. So we've come to the end of the session. I hope this has been really useful to you, that you've learned something from here, and we're going to have a break now. We're going to have a 10-minute break. There's going to be ads, etc. Just like last time. I will see you on the other side of 10 minutes. Ciao for now.
SUNY Canton is a small institution in northern New York. We have approximately 3,200 FTE students, approximately 450 faculty and staff, and the campus itself covers approximately 500 acres. The network infrastructure is the foundation of everything we do. We've talked about online student engagement, our esports initiatives, our live streaming efforts. Everything that we do on campus relies on that critical infrastructure. And Extreme has been able to provide that and provide the support from design to rollout to support. We currently have one IT staff member that manages the entire network. Overall, our organization is fairly small. We only have 18 full-time employees. At any given time, about 4,000 people on the network. That varies throughout the year because we have a large summer and winter term. Each user typically has 4 to 5 devices, so we do see a significant volume of devices on our campus network. We had an aging infrastructure, and we had a need for additional bandwidth and additional Wi-Fi coverage on our campus, and those were the primary drivers into us moving towards a full campus-wide upgrade. Since we deployed Extreme, we've had the ability to better manage our network from a security standpoint and also allow more access to personal and Internet of Things devices across campus.
Esports is the competitive experience of playing video games. So much like we would play baseball or football in an arena, we play our sports online in virtual battlefields or virtual arenas. Esports has grown to become a multi-billion-dollar industry across the world, with the majority of the players coming from East Asia. However, the strongest game market being in the Western Hemisphere, United States.
Extreme has done a terrific job in helping SUNY Canton grow its esports team and get our name out there. So it's been a great partnership for us. They've helped us with our marketing, and we've partnered with them on a number of different initiatives that have went really well and gotten SUNY Canton's name out there, helped us build our reputation in esports. So Extreme has just been a wonderful partner, and we couldn't thank them enough for helping us really get things rolling over the last year and a half. We are a mix of students both on campus and online, and so that was one of the reasons why we decided to start an esports team, is we wanted to give our online students the opportunity to participate in athletics as well. If you take a look at what traditional athletics brings to a school, esports brings pretty much all of that as well. So they do better in the classroom, they have higher retention rates, they have higher graduation rates. The students seem to be more fulfilled. They are with a group of students who have similar interests. Esports has dramatically helped our enrollment and our retention numbers. Students come here, they want to play esports, and they want to be involved.
Extreme Networks GTAC support has been fantastic. In my opinion, it should be an industry standard. Our local engineers and account reps have been fantastic, available virtually 24/7. I can't speak highly enough about the folks at Extreme that I've dealt with, and I think that's the differentiator between other technology vendors and Extreme Networks. For us here at SUNY Canton, Extreme Networks has been the right choice.
My name is Akio Sugeno. I'm a VP of the engineering. Company name is Telehouse. And we provide a data center on about 48 cities on the globe. But we also provide Internet exchange point service in New York and Los Angeles. That's our unique point as a data center provider. As our exchange point operator, our customer is always demanding. Our customer is like Google, Amazon, Apple, Facebook. We want to make sure we provide enough capacity at shortest latency. So port density is pretty important. Now customer is demanding 100 gig ports, so we have to provide hundreds of 100 gig ports for their needs. And we currently have over 1,200 customers, and our peak traffic is 600 gigabit per second. So we want to make sure our exchange point is running stably. Currently, we use SLX routers, and the reason I chose XLX is the port density of 100 gigaports, and it speaks MPLS with VPLS, which is like a key engineering feature we need. Also, it runs SLX operating system, which is based on Linux. So that means we can write code, we can automate everything. The 100 gig port is key feature we needed. Also, faster latency of SLX provides is a key for our demanding customer like Netflix. They're demanding shortest possible latency to deliver their TV contents to the end users. That's kind of key point for us. Extreme has like a dedicated our team. They know us, they know our configuration, software version, everything, and they do have a lab emulating our environment. So whatever happens, they can emulate. They know what we have, they know how we operate. I don't have to explain anything. This is a kind of issue. It's a great service. Besides IIX operation, which demands higher speed, like 100 gig, we are also shooting for the cloud connectivity service. The enterprise market needs lower speed, like 1 gig, however, more port density at lower cost. That's kind of our challenge, and I'm sure Extreme can provide such services.
Okay, we now have done layer 1. We then did layer 5, 6, and 7, the application layer. Now we're going to come one down, and we're going to work on understanding layer 4. We call that the transport layer. So remember, when an application wants to talk, it starts at a certain point up at the top application layer, and then it's going to go down the OSI model onto the Ethernet on layer 1, go across the network, and then come up the other side and just reverse the work that happened on the source side. So we've now done the top 3. Now let's move down to the next one. Okay, let's check the time. All right, we're good. All right, data transport layer. Okay. So once again, let me read what the objectives are for this particular module. To understand the principles of the transport layer, to understand the differences between source and destination ports. So remember the story of the hotel. Someone is staying at a hotel. You might see them and know that they're staying at that hotel, but you don't know the room number, right? The room number is specific, is very specific. And so the room number in computer terms here is talking to the port number. So which is the source, which is the destination, which is the original port, which is the destination port. That's what we're talking about here. To understand the differences between connection and connectionless protocols. This is quite an interesting topic, and you'll see when we get to it. It's really easy to understand. I have a really cool animation, makes it really quite easy. And then to distinguish between common networking protocols. Okay, so those are really quite easy. This is quite a short module, like 20-odd slides. So you're going to knock this off, and it's going to be like a piece of cake for you after having done the OSI model. This is a total piece of cake. So don't fall behind now. We've got 20 minutes to go, more or less 20 minutes to go. Stay stuck on this, have a glass of water, drink something if you need to, because this will bring us to land today's session. It is an interesting one, though. Right. Now, physical data network layers, as we've discussed in the OSI model, they are useful to allow devices in the same or different subnets to communicate. So remember we spoke about a LAN, and we said a LAN is kind of an area, local area network. It could be your house. Smallest implementations, probably your house, couple of computers, mobile devices, etc., etc. And it can go much bigger than that, of course. A LAN can, but generally that's kind of is what it is. But physical data network layers, they are useful to allow these devices to connect with each other, to communicate with each other. We know how we can reach each other to speak. So we've spoken a little bit about IP addresses. Later on, or in the next session, we're going to cover MAC addresses, and then we're going to cover IP addresses in terms of when you need to get something onto the internet outside your little local area network. So transport layer allows you to specify and control particular services and applications when traffic is being transmitted. Just like in human language, when I'm talking to you, I can't just go, if I don't want to be boring, I can't just go at the same monotonous tone for the whole of the conversation, right? I have to control. So I've got time that I need to control. I have to control my attenuation. I need to get louder, softer. I need to draw you closer, listen up, there's various ways. So layer 4 attempts to do those types of things, to control the conversation flow. Now, the two most common protocols, transport layer protocols that operate on this layer, on layer 4, the transport layer, are something we call TCP, which you already would have had a pretty good idea on course 1 when we see TCP IP, kind of a common language. So TCP is one of those protocols, mega important for the internet and for networking. So TCP, and the other one is UDP. Okay, TCP and UDP. Do you need to know them? Yes. Will they be in the exam? I'm pretty sure that they will. Are they complicated? No, they're not necessarily complicated. Nothing is complicated if you dedicate some time to learn it. So nothing is particularly complicated with these two. But the vast majority of devices connected to the internet, from your IoT sensors, that sense climate change, to the refrigerator you have that's connected to the internet, to IP radio, to television, IP television. In fact, just about every device connected to a network that communicates with a network is running one of these two protocols. Okay, so popular, everything is using this stuff. Transmission control protocol is something we call a reliable protocol. We sometimes talk about guaranteed delivery, right? So if I want to send something to a mate down in South Africa, the other day one of my friends asked me to he bought something here in the UK and they didn't deliver down to South Africa, so he said, "Hey Isaac, can you hold it at your place and then I'll get a courier to come and collect it." Why a courier? Because he was pretty sure that if I just put it in the post office and sent it to South Africa, it would never get to him. Not once it's landed there, it would never, not easy. But if he sent it by courier, it would cost him a lot more money, but the guaranteed delivery. And he was willing to pay for guaranteed delivery because it was important to him. So in a way, this is the same type of thing. We have two protocols, and TCP, Transmission Control Protocol, is one of those, like the courier. It costs more in terms of time, perhaps, to process it. It's got more overhead on it, but the advantage is guaranteed delivery. UDP, post office. It's not guaranteed. It might get there. Yeah. It might get there, but it might not. That's how it works. And in guaranteed delivery, just like when I take a parcel and I took a parcel to the courier, they asked me to sign. They signed, that they'd received the parcel. If the courier comes to your place, they give you a slip that they've received on this day at this time, and this was the person. So, you get given that, and then you can take that and you can go onto the internet and you can track that package, and you can track as it leaves, the depot, and it goes, to another main depot and then to the airport. You can track that stuff online. And TCP kind of is something like that, because as the destination receives the pack, it kind of acknowledges it. So yes, the first depot, have you acknowledged that? Have you received it? Yes, I have. Goes to the second one. Have you received it? Yes, I have. Goes to the airplane. Has it been loaded on the plane? Yes, I have. And off it goes. You sometimes see something like this on Amazon. When you order Amazon on your app, you can see, it's 7 stops away, and the minute somebody drops off a package at your house, and you kind of sign for it, or they take a photo that you've delivered the package, a minute or two later you see a little notification pop up on your phone, say, "Hey, thank you, we've delivered the package." That really is an acknowledgement. So do we kind of get that? TCP is we call that a reliable mechanism, because there's always acknowledgements along the way, along every stop, that I've received this packet. So we pretty cool. So let's look at this animation. I really like this animation. Spent a lot of time on it, but I think it kind of explains really well the difference between two. So let's look at TCP. Remember, TCP we said was a guaranteed mechanism. So with TCP we take data, right? And the data hits the wire, you can see it traveling down, and when it gets to the other side, an acknowledgement was sent. It says, yes, I received that packet, send the next one. Watch, I send the packet, it says, great, I received it. It sends an acknowledgement. I send the data, it sends an acknowledgement. Got it? TCP. Look at the difference with UDP, because it is quite a big difference, right? Look what happens with UDP. There's no acknowledgement, right? It just takes data and it shoves it down that pipe. Whether you get it or not, it's not interested. It just, it's like the post office, just chuck it in and let it go. If it gets there, it gets there. If it doesn't get there, it doesn't get there. And you might think, gee, that's really dumb. That doesn't, why would anybody do something like that? Oh, I'm glad you asked. There's many reasons, but let's look at this in a little bit more detail. So TCP, UDP, both of these are going to have, if you remember, if you have a computer in London, you've got a computer in Lisbon, you need addresses, right? So a client browser, a local client browser, would have an IP address, right? An IP address. Now remember, an IP address, I said, is like a kind of a phone number, and I kind of said to you, it's like 19 some. So we'll look at an IP address here in a short while. So a computer will have an application, and the application will use a port number. The combination of IP address and port number, the combination of that is something we call a socket. Okay, I know it's like a lot of different terms, but just think of a socket, of a socket plug that plugs into the wall. The combination, one is called an IP address, one is called a port, but if you join the two together, plug it into the socket, we call it a socket. So here is an example of an IP address, 192.168.44.72. Then you'll see that there's a colon, and then it says 49152. Now, that colon 49152 says, hey, the colon indicates here's a port number. After me is a port number. Now, generally speaking, you never see this when you go into a browser, because you just type www.extremenetworks.com. That's all you do, and off it goes. The DNS takes care of the rest. But sometimes you might know the address of a router. Like I know that the address of my router at home is 192.168.something.254. That's what the address of the router is. So I know, and I can just type that directly into my browser. And if I know that it has a specific port, I can just put colon and the port number. But normally it's just port 80, which then browsers use as default. So I kind of understand what that is, the client browser, etc., etc. And on the destination, in this case a web server, it could be the one that hosts Extreme Networks website. There again, I'm going to have the same thing. I'm going to have an IP address for that machine, right? And if it's HTTP traffic, it's traveling on port 80. So if it's a web server, and if you want to talk to the web server, standard port 80. If you wanted to talk to that web server securely, HTTPS, not for plural, S is for secure, then it would be port 443. Now, each stream of data that flows, that's got to be transferred, it will be broken up into one or more packets. I mean, it will be quite difficult to just transmit one packet. Maybe if you send a WhatsApp message and you just say, K, I'm okay, K, and you send that, maybe that will be just one packet. But generally speaking, it might be, if you have a message, if you type an email, it's going to be lots and lots of different packets that need to flow. And these streams are going to be identified by two port numbers. And these port numbers are going to be in the range from 0 to 65,535, right? When I say two port numbers, because there's going to be one on the source machine and one on the destination machine. Now, the source port identifies the session. Remember the application, the session, when it establishes a session, it's going to identify the session, the application, Outlook, browser, whatever, on the source device, right? That's the source port. That's what it's going to do. And the destination port identifies the port on the destination machine that I want to talk to. So if I know that a web server operates and listens on port 80, then when I connect, the destination port will know, oh, okay, this is an HTTP packet. That means that packet is going to port 80, unless I specify differently. Generally, you wouldn't do that. And if I'm talking to a bank, to the web server of a bank, then it's definitely going to be port 443, correct? Because it's the HTTPS secure. So we kind of now understand these two. Destination ports. The destination port is chosen from a range of well-known ports. So if you were a bank or if you were Extreme Networks, you couldn't be silly and say, oh, you know what, we don't want to do the same, port. We don't want our web server to listen on port 80. We would prefer to listen on port 661. Okay, that would be a problem. Firstly, there's a standards organization called IANA, and they issue out these reservations for standard ports. So IANA will say port 80 is for HTTP. Port 443 is for HTTPS. So they make these rules, and you can't mess with that. So if you just come up with 661, it might already have been assigned to another port, and that would create a problem. The other problem you have is, how does the browser in your home or on your phone know that it needs to connect to Extreme Networks on port 80 on port 661? It doesn't know. So you could write an app to do that, but if it's just browser, no. So stick to kind of the standards. These ports, like I said, 0 to 1023 are assigned by IANA, but generally speaking, port 0 is not used to talk between machines. You can use that to talk just within the computer itself. Source ports, from the source computer, they are chosen from a range of what we call ephemeral ports, which are based on higher numbers. And those higher numbers are 49,152 to 65,535. Those are the numbers that ephemeral ports are chosen. And what does ephemeral port mean? It's chosen for a short time only. So your source device wants to send a message to a destination. It knows, oh, that's port 80 that it needs to talk to. That's the destination port. What port am I going to use? Anyone between 49,152 to 65,535. I'll choose 50,000. Cool. It doesn't really matter, right? You're never going to have 25,000 applications running all using the same. So it just chooses a random one. It says, cool, I'm going to choose that particular port. Yeah, quite easy to understand. UDP. Remember the one where packets just flew? There was no acknowledgement. UDP stands for User Datagram Protocol. This is important. User Datagram Protocol. This might appear in an exam. I'm not saying it does, but it might. Allows a protocol at the application layer to send packets to another application without establishing a connection. So it doesn't shake hands, it doesn't care all of that, it just sends packets. That's it. That's all it does. It just sends packets. We call that connectionless or stateless. Connectionless or stateless. It doesn't really establish a connection. It just talks, right? It just talks. That's what it does. And again, I'll show you how these things are useful. If it loses a packet, if a packet is lost in transmission, and by packet we mean a packet containing data. It also contains headers and things like that, but think of it as a packet containing stuff, data on the inside. If a packet gets lost, I don't care. I don't care. I'm just going to say, this packet, oh well, too bad. The next packet, and here's the next packet, and the next one, and the next one. It relies on other protocols. If it needs to be reliable and secure, it allows for other protocols to be used if required. But if you want the reliability, UDP is not the app for you. I really like this particular slide. Sleep with their face down because it's too heavy for their bodies. Aussie the L. Okay, so UDP, connectionless protocol, stateless protocol. Here's what the header looks like. The header just being what you attach to the packet, right? And it's very simple. Source port where's it coming from, which is the destination port it's going to. So any machine that picks it up just needs to say, well, you know, you're going to be talking on this particular port. It has a length, whatever that length is, and then a checksum. Checksum is something that I want to cover in more detail when we do the next module, so that'll be something next week. It's really an interesting thing, and I can show you something so interesting in 5 minutes. I'm not going to talk about it today. Sometimes it's called a CRC, cyclic redundancy check, so we're not going to get into that today, but you can see the header for this is very lightweight, very simple. Okay, and that's what makes it fast. So the transmission control protocol, UDP, we've spoken about that. Now transmission control protocol, abbreviated TCP. Before you can talk to a host, by that I mean something like a web server. So you type in www.extremenetworks.com, that whole DNS process I told you about, that kind of happens, blah blah blah. But before you can actually start talking and saying, you know, give me that website, I want to see that Extreme Networks website, it's quite polite. It starts with and initiates with a three-way handshake, right? So it doesn't just start blurting out. It does this handshake before. So, you know, are you there? Yes, I'm here. Well, I'd like to talk to you. Well, okay, I acknowledge that I've spoken to you, that I've received what you've said, and do you get me? Are we okay? Yes, we are okay. And after that, then the conversation starts. So that's quite different to UDP, but there's a number of things that are the same, right? It still has to specify source ports. It still has to specify destination ports. Which port? I mean, you know, UDP still does that. UDP still has source and a destination port. Internet protocol on both of these protocols. Internet IP, that is the protocol on which all of this is layered. So the underlying protocol for both of these. And here's the thing: TCP has more overhead. So because what you're trying to do with TCP is guaranteed delivery, because you're trying to say, I want this to be like a courier, I want to ensure that all the data that I send goes and gets to the other side, like a bank transaction, right? You don't want, you know, your bank to remove a few zeros. You wouldn't mind them adding a few zeros, but removing as zeros, like, no, we don't kind of want. So we really want, when we talk to a bank, when we talk to something secure, we definitely want to use TCP. Remember UDP, stuff like Skype chat, video chat, movies, oftentimes, you know, single frame, if you lose it, so what? Your eye doesn't even notice that at all. But your eye will notice if there's a few zeros missing on your bank account. The sequence number that we talk about here, this is that sequence number. In fact, you know what? Instead of me talking more about the sequence number, why don't we just watch a video clip that I recorded a while ago, and it's on the YouTube channel, and it talks about the three-way handshake, and that kind of explains sequence numbers quite well. So Claire, if you can just hit play on that video at this point, and then we'll come back once that is finished. When I call Manuel and he answers, our conversation actually starts with an initialization sequence. In networking, it's exactly the same thing, but we call it a three-way handshake. To learn more, hit that subscribe button, hit that notification bell, and I'll see you on the other side of this. Manuel. Hi. Yes, it's me, Isaac. Yeah, I can hear you. Hey, I'm great, man. How's things down there? The conversation that I had with Manuel, when I called him and he answered, I sent him a message. I said, "Hi, Manuel." On his side, he acknowledged that and he went, "Hi, who is that, you, Isaac?" And I said, "Yeah, it's me, it's Isaac." After we had gone through that sequence, we then began our conversation. And so in networking, we do the same thing. When I, as a client, my computer, as a browser, for example, when it navigates to www.extremenetworks.com, it sends a packet. It needs to synchronize, initialize this conversation between myself and the web server. So it sends a synchronization packet to the web server. When the web server gets it, it does what Manuel did. It acknowledges that. It says, "Hi, is that Isaac?" So I send it a synchronization request. It acknowledges that and sends back its own synchronization request, and I then acknowledge that synchronization request. And from there on, we start a conversation. In networking, we like to talk about reliable connections and reliable protocols, and one of them is TCP, the language, the common language that we use to move information across the internet. So when my client talks to the web server, it's going to send lots of packets, lots of requests. And when the web server gets them, it needs to know how to sequence them, how to reassemble them on that side. So when I say hi in human language, I just say, "Hi, Manuel." But a computer says, "Hi," and it says, "My sequence number is 10,000. Just a random number. The server on the other side, when it receives that packet, it acknowledges packet 10,000, and then it says, "Hey, I acknowledge this packet, and I'm now ready for packet 10,001." So it increments that sequence number by 1, and at the same time it sends its own SYN. So I send a synchronization request, a SYN information, to initialize this conversation. The server gets this request, acknowledges the sequence number, and then generates its own sequence number so that my client can keep track of its information, and it sends that, and we call that a SYN-ACK. So I send a SYN, the server sends a SYN-ACK. When I get it, it says, "Oh, it's received 10,000, it's now looking for 10,001. And it sent its own SYN with a random sequence number, let's say 60,000. So I then acknowledge the server's sequence number, and I say, "I now acknowledge that packet 60,000, and I'm now ready for packet 60,001. And from that point onwards, every packet that goes between our two machines will have a sequence number that's incremented by 1. That is called the three-way handshake. Okay, pretty cool. Thank you. I hope that you got that. Just one last thing about sequence numbers is, if packets are sent from one side to the other side, they all have the sequence number. Sometimes it can happen, well, not often, but it can happen that a server will get the packets out of sequence, right? They'll get packet 3 before they get packet 2. In that case, because they have sequence numbers, it's easy for the server just to wait until it gets the right packet and then insert it into the correct order. So brilliant mechanism, works really, really well. A lot of transmission control. Okay, so that's the big thing, and there's the overhead. If you've ever watched kids playing broken telephone, so those of you who might not know, in fact, I think kids all over the world play this game, right? Broken telephone. You tell a kid, you've got 5 kids, and you say to one kid, the message is, the color combination is red, blue, green. Right? You tell that to the kid, and he goes to the other kid and says, the color combination is red, blue, orange. And that kid goes to the third one, is the color combination is 5576. And the last guy says, oh yes, if I ask him, what did he say? What message? He says, oh, you should give us all chocolate cake, right? It gets totally scrambled because there's no error check. They just pass on the error. So if I make an error, you make an error, and then the next one makes an error, and there's no integrity in the data, right? So if I say to the first kid, the color code is red, did you get it? The kid says, yes, you repeated. You told me that the color code is red. I acknowledge, yes. Okay. He then tells the other kid the color code is red. Oh, okay. Can you acknowledge that? Yes, you said the color code is green. No, I said the color code is red. Oh, can you send you meant the color? And so if there's all that acknowledgement, slower, more overhead. But the last kid won't be telling me they want chocolate. They will say the right thing that I told in the beginning. So are we good on that? Perfect. Reliability. The other thing that I really like about TCP, and we are coming into land now, is flow control. So flow control is a really fantastic thing, because if I had to initiate a connection with you, let's say I phoned you and we were chatting and I said, did you get what I said? And you know, the response was, yes, I got what you said. Okay, so how do you think about, did you get what I said? I got what you said. You said, oh, and what do you think about? And if we go backwards and forwards, and every time I say a phrase like, did you get that? And yes, I got that. Can you say the next sentence or the next word? So, well, what about? Did you get that? Yes, you said, well, what about? It would be nightmarish. And so computers are exactly the same, because they're based on human behavior. What do we mean? Flow control. So flow control says, send me a packet. I send a packet, it acknowledges. Okay, send me a packet. I send a packet, it acknowledges. Said, hey, try sending me 4 packets instead of 1. I send 4 packets. I check them. Say, yeah, I got 4 packets. Hey, try sending me 8 packets now. Send 8 packets. Got it. Says, checks it and says, oh, no errors. Okay, send me 16 packets. So I send 16 packets of data. It checks 16. Good. 32. Give me 64. Give me 128. Give me 256 packets. So instead of acknowledging every packet, I now acknowledge bunches of packets, you know, and that's why when you download a file, you start and it says something like, this will take 45 minutes to download. Like, oh, I can go have a cup of tea. You look again and it says, oh, this will take 16 minutes to download. So, oh, no, that's cool. I'll wait for it. Then you look again and it says, oh, there's going to take 2 minutes. Wow, I got a really great connection over here. And you look down, well, it's nearly done. Oh, 30, what on earth? This, what's happening? Well, it's exactly flow control. Your machine sent 1 packet, server said, cool, send me 2, 4, 8. Your machine keeps sending this. 45 minutes, that's how long it's going to take. But you do 256 packets, you do however many, right? And it's just flowing beautifully. Then something happens, there's interference on the line, there's something that's gone wrong, you know, a lot of bandwidth has been taken up by somebody watching 4K TV. Ooh, it slows down, you know. So it goes, that's how long it's going to take, that's how long it's going to take, oops, that's how long it's going to take, that's how long it's going to take, that's how long it's going to take, and then it kind of settles, and then they kind of find a speed that works reliably, and then they kind of stick to that. So flow control, absolutely brilliant. The last thing that I'm going to talk about is just multiplexing. And multiplexing is, if you're anything like me, when I open up a browser tab, I can't just have 1 tab open. I've got to open 30 tabs at the same time, right? And all of those are connecting to different websites. I've got my Gmail open. I've got my Extreme, Extreme site open up. I've got the document site open up. I got the curriculum site open. I've got all of these. They all requiring ports. They're all talking. I got my banking site open up. I got 1 or 2 other sites open up, and they all have multiplexing, right? So they're all using port 80 to connect, but they're all running within a browser. And multiplexing allows that. Many applications within a single host to use the protocol concurrently, all at the same time. Sometimes I even have 2 or 3 browsers open, all using that. So that's multiplexing. So fantastic technology. You can also, provide like quality of service and say this is more important than that treat this with urgency. What a great protocol. No wonder this has been invented 40 years ago, whatever it is, and we're still using it today. It is so flexible in what it can do. Don't stop here. If you want to read more, there is plenty more for you to read on this protocol. There's a site you can go to called TCP Guide. It's really comprehensive. You can find a lot of good information. Equip yourself. Study more about this. It's a fantastic protocol for you to learn. TCP guaranteed delivery, right? simply because if you don't get what I sent you, please send it again. And if you still don't get it, I'll repeat it again. And if you still don't get it, I'll repeat it again until you get it. Okay? So great protocol, fantastic. Okay, let's look at the header, and then that'll be the second last slide, and then we'll come into land on here. So the header, as you saw for UDP, was just 4 little sections, right? Source port, destination, length, and then it had a checksum at the end just to make sure that the data was okay. So very simple, very low overhead. TCP, not so simple, a lot more overhead. But essentially, some of these things are the same. Source port, destination port, those things are the same. Sequence number, UDP didn't have this. So sequence number that I randomly generate from my side, and then an acknowledgement number from the server saying, yes, I acknowledge that, and this is the number of the acknowledgement, and off we go with those. So you see those here in the packet. The other thing that you see is over here, this little bit, the ACK bit, the acknowledgement bit. If that's busy in a communication, that bit's going to be turned to 1. If the SYN bit is being used, it's going to be a 1, right? And the FIN stands for finish. That one is going to be a 0. As long as we're communicating, that bit called finish the session, that's set to a 0 until I'm ready to end the connection. When I then finished with Extreme Websites and I then type in a new website, that session that I've established needs to be finalized. It needs to be finished. Okay, so when I'm ready to do that, I'm going to send a fin packet, or the fin bit in the header is going to be now switched from a 0 to a 1, saying, hey, I'm ready to go. Got it? Perfect. Here's the checksum. Still got the checksum. Urgency, if that packet needs to be treated with urgency, you can also, it's 16 bits worth of content that you can switch on, etc. So the TCP header between 20 to 60 bytes. So that can be quite big, and hence the overhead, and hence why people say it's slower. So here's kind of a graphic to show you. I start by wanting to talk to a web server. So this is that 3-way handshake. I send the SYN packet, the synchronize. Let's synchronize to the server. The server acknowledges that and sends back its SYN packet. Let's synchronize. I acknowledge that. And then once that's been acknowledged, I then send an HTTP request. Okay, now send me that web page that I requested. So this process goes backwards and forwards. Okay, send me this, send me this, send me this, send me this. The server's, here you go, there's a response. I send the request, it sends the response. And it goes on and on and on and on and on until I'm ready to browse away from here. Okay, to go and look at the football score or whatever it might be. When that happens, that bit in that header gets changed to a 1, and it says, oh, I've got to be notified that we're going to finish this connection. Okay, so the server then acknowledges, I acknowledge you sent me a fin packet, and here's my fin packet. I acknowledge, goodbye. And we've got to the end of the session. So I hope this has been really useful for you. I hope you've enjoyed it. I've certainly enjoyed teaching it. Read more, go learn more. This is fantastic stuff. Right. Homework. Just like last week, you're going to see a notification about homework. Go find the homework in the materials section of the Meeting Pulse app. And again, like last week, it'll have five or six slides. Please don't ask us about sending it in. You don't have to email it to us or anything like that. I'm not going to mark your homework. Just do it. And in the next session, I will produce a little video that shows you how we got to the answers of the homework. Thank you for attending. Thank you for giving me 2 hours of your time. I know your time is precious, and I value that. We treasure that at Extreme. Tell your friends. If you liked it, like us on social media, like us, put comments on the YouTube, channel or whatever, on LinkedIn, on the Extreme account, tag us as Extreme Academy Live or hashtag Extreme Academy. We love those things. We like to see your feedback. Thank you once again. Be safe. Have a great week, and I'll see you back here next week, same time. Cheers.